How did you do? Okay, let's get started. So just so you know what we're doing today, we're going to finish up maybe 20 slides to go through. We'll go through them pretty quickly and finish up chapter 10. Then we're going to do a little review for the final exam and go over some materials for that. Let's see. I did send out an email on Blackboard that for the chapter 10 Mastering Chemistry, it's an optional assignment. So if you do it, it will replace a lower grade. If you don't do it, and I gave you until Sunday. How long did I give y'all to do that? Sunday, is that right? Saturday. Okay, whatever the date is, whatever's posted, you can look at Mastering Chemistry. It tells you the due date. I don't remember off the top of my head what it is. So I would suggest that you take a look at that as part of your preparation for the final exam. Okay, so just let's finish up with the notes right quick. So first thing is I want to talk about is how do we deal with a multiple central atoms. So what you do is you simply, when you have things that have many interior atoms, you do it one atom at a time. That's what it comes down to. And you just work down the chain. So we think of just in an example, if we have this molecule on the bottom, which this is acetic acid, this is a relatively simple molecule, less than 10 atoms in this system. But we go to the first atom, we look at it, and we see that it's an AB4. AB4 is a tetrahedral. So we go down to the next atom, if we go down to the chain, and we see that the atom in this one is a AB3. So on that one, it's a trigonal planar. And then we go down to the next atom on the chain, and we look at this one, and it's an AB2E2, and that's a bent. All right, so from that, we could predict a structure. Now, I just realized this is not that molecule. So this, if we're going to draw this one, this is ethanol. Okay, so it's a different structure. So if I'm going to draw it as a stick structure right quick. So I would do the tetrahedral. So if I'm going to do it in a the manner that we just talked about, so I'd have one hydrogen projecting out, so solid, one hydrogen projecting back, and then go into the plane. The next one would be a trigonal planar. So I would have my double bonded oxygen here, and then go to the last one, to the bent, to the oxygen. So we'd have a bent, and we can just build on it and start to get three-dimensional shape of what things look like. So you take it one atom at a time is what it comes down to. Right, so this example of a multi-atom system is boric acid. So boric acid, if we look at it, it's got the boron's a central, is the central atom, and then each of the oxygens have a hydrogen connected to it. We look at the Lewis structure with it. The central atom is an AB3, so it's just a trigonal planar. Then each one of the oxygens is similar to what we usually find in oxygen. It's an AB2E2, so that's a bent geometry. So from that, we can come up with a shape that's a tentative shape for what boric acid may look like. Okay, so we can build on these things. The last topic that we want to look at in the chapter is the concept of polarity. So whenever we have charge separation, it's possible that we can have a molecule be polar. So to be polar, it has to have polar bonds. We identify that with the difference in electronegativity, and that's something that's theoretical. The way that we see that or determine that in the lab is we can measure something called the dipole moment, which is a numerical reflection of
how much charge separation can occur. The second thing to be a polar molecule is there has to be a lack of symmetry or an unsymmetrical shape. So if everything's symmetric, what happens is everything pulls in the opposite direction and everything cancels out. We need a lack of symmetry in some way. And we'll look at some examples of that. The polarity of a molecule influences its intermolecular attractions. Things like the boiling point and solubility come into play. It is critically important to influence things like bonding between amino acids, bonding between base pairs in DNA. Just in nature, it takes advantage of these intermolecular forces, and it governs life as we know it. The non-bonding pairs, the lone pairs, also influence the polarity of a molecule because they pull electron density in their direction. So here's just a simple example. Here's the hydrochloric acid molecule. So it is a polar bond because of the difference in charge separation that occurs. If we look at the electronegativity differences, so chlorine was 3, hydrogen is 2.1. That's the electronegativity numbers. That means that the electron density is attracted in this direction around the hydrogen, or around the chlorine atom. And the way that we represent that in a hot-cold map is with these partial negative and partial positive charges, representing the partial negative as a place there's going to be high electron density around one particular nucleus. Okay, so when we look at, you're here today, you get a clicker. All right. 21. So I hope you didn't click for somebody else because I'm fixing to count seats. Okay, so missed somebody or you snuck in after me. The way that we follow up how these this bond polarity adds up is we need to think of some geometry or some way that we can put these things together, and we call it vector addition. So just the very simplistic vectorial addition is when you learned about vectors starting in like 7th or 8th grade, and we're going to treat these dipoles that exist in molecules like vectors. So if we have a vector that is going to the left, and we add another vector going to the left, and they each have a magnitude of 5, the resulting vector is also going going to the right. I'm looking at the opposite direction. So the resulting vector would be going to our right with a magnitude of 10. So they're going in the same direction used to add the two things together. And if you have some that are going opposite direction, they're going to just cancel out. So you choose a central point. In this example, I've got vector A that's going to the real left at a -5. Vector B that's going to the right at a +10. They're put together where 5 of this one cancels out 5 of B. The result is 5 going to the right. And if the possibility exists that the two vectors are completely canceling each other out, a -5 vector and a +5 vector would result in a vector addition of 0. Okay, now that's the easiest way if they're all going along the lines. Sometimes they're going on angles. And that's what commonly happens when you have things that are in different types of bonds. So if it's occurring at an angle, what you do is you take the vector A and you break it up into the components that describe any vector. So if I think of this as an XY grid, I've got a Y component associated with A, all right, and I've got an X component associated with A. So I can think of the X of A component, all right, or that would be Y A component, and a X-axis A component associated with that vector. And then I could do a similar type thing with B, except what happens with vector B is it's all on the X-axis, so that's all the answer is with vector B. But to get the result, I just add these two things together. So I take this amount, add to the end of this one, come out that distance. So now my total that I'm going to go in the X directions here, in the Y direction, I add the totals for the Y puts me up to here, and it gives me my resulting vector that I see. Simplistic vector addition. All right, so if I do something like on this example on the other side. So if I look at what we've got with A and B, I've got an up component that's in this direction. I've got a left component in this direction. Okay, if I look at vector B, it also has an up component, maybe just a hair higher, and then it has a big right component to it. So what happens is the two up components are going to add together, so my resulting vector is going to be going up, so maybe up in here. And then I've got this portion subtracting away from the total of this one, so maybe something like that. So my resulting vector ends up being this point. This is my result that I get. And you always take and just add two together at a time. If you've got three, add two together, get a result, then do the third one. All right? If you want to break it into three pieces, you can. So if we look at how we could do multiple vectors in these and start adding things together, we look at, here's a three-component system. So what I would do with a three-component system is I would first put together vectors A and B, right? So it's easier to see them in your mind if you do it two at a time. Then I would get result R, and now I've got R I need to add to C. So I've got something pointing up here and something pointing here, so the results, part of the up is going to cancel out. Right, so if I look at the magnitude on that one, I've got this result that's got an up component and an over component. And I've got to add it to this down component and this over component. So those two things are going to come together and take me this way. And then I've got to put these two things together. Looks like this one's maybe a little shorter than this guy, but it's not much. So there may be a tad up component to it. That's the result. And if in the case that if you have something that's perfectly symmetric, and this example would represent something that's trigonal planar at the bottom. So if I have this component where I have a left-right addition to it, I add those two things together, and the left component and the right component would completely cancel out. So I've got this component and this component, and then I've got an up and an up. The left and right would cancel out, and the resulting would be this up vector. But now I add this up vector and this down vector, which is the same magnitude, and the result of putting something that's symmetrical together is that everything cancels out. It's zero. So whenever you have something that's perfectly symmetric, like a trigonal planar, and if all the bonds are equal, it's going to be a nonpolar molecule. There's no net dipole moment. Everything cancels out. Right? That's a very simple introduction to vector addition. When we look at it in now our common geometry result we have, if it's a linear molecule and the atoms are the same, that's going to result in a nonpolar molecule. Right? If the atoms are different on each side of the central atom, it may or may not be polar, depending on what the difference in electronegativities are. Okay, so if you've got something over here that's got electronegativity of 3.5, and something over here that's got a electronegativity of 2.1, okay, then that's going to be a polar molecule because it's not equal poles pulling away from each other. Whenever we have something that's a bent geometry, almost always with a bent geometry, it's going to result in a polar molecule. Okay, because the net dipole moment is going to be pointed in this up direction. When we have an example of one like the trigonal planar that we looked at, and all the atoms are identical, that's symmetry. That's going to be a nonpolar molecule. If we have a tetrahedral arrangement and all the atoms are identical, it's going to be a nonpolar molecule. Everything's going to pull away from each other and cancel out in symmetry. However, if it's trigonal pyramidal, what happens with a trigonal pyramidal is that if you got a central atom up here and you have electron density pulling towards the exterior atoms, so nitrogen trichloride, even though there's a long pair of electrons up here, the electron density is pulling in this direction away from the central atom. There's a lack of symmetry in that one. Okay, so put this one together. Break it into the XY components and add these two vectors together. Tell me the result.
Is the first number the x value?
The first number, yes. So this is traditional XY coordinate system. So the first represents X, x-axis, comma, Y. So X, Y. What do you want? Okay, I miscounted water. Right. Put your guess in. Last chance. So most of you said it was B. So if I look at just the components, show you quickly how I would do that. All right, so if I'm going to take this vector first, it's got a -2 component, or a +2 and a +4 component. If I look at this vector, it has a -2 component and a -4. So on the X scale, I've got to put together a -4 and a +2. So I'm expecting the X value to be -2. All right, and if I go to the Y component, I've got a +4 and a -2. So I'm expecting the Y component to be -2. So looking like should be probably choice B. That's simple vector addition. Yes.
Where'd the 4 come from? On the 2? On the X, Y?
On the Y, so I took this vector and I broke it into this component, which is +2, and this component, which is +4. Does that make sense?
Okay.
Okay, so this one is that value. This one is this value. Okay? All right. So now we want to think of this idea where we figure out where the electron density is, where it's being pulled. Is a molecule polar or not? So in the example of carbon dioxide, it's an AB2. What happens is that even though the carbon-oxygen is a polar bond, the fact that there's complete symmetry in the molecule, it's linear, the two opposing dipoles completely cancel away out with each other so that there is an even distribution of the electron density. So there's no net dipole moment. You do have a dipole here, and you do have a dipole here, but there's no dipole moment for the entire molecule. When you have that case, that's the result of a nonpolar molecule. The thing to look for is symmetry. So are all the atoms the same? Is there an equal alignment among things, whether it be in a linear shape or a trigonal planar or something that allows everything to cancel each other out? Whenever we end up with a net dipole moment, with an example of the water molecule, this is what gives water its unique properties, and we'll start talking about some of those properties going into chapter 11 next semester. It's this charge separation that occurs because of the dipole that's pulling towards the oxygen atoms from the hydrogen on both, ends up with this being a net dipole moment when you put these together going in this direction. So now you have one region that's electron rich, so it's electronegative, and you have a region of the water molecule that's electropositive. And this gives water its very unique properties that we're going to learn about. All right, so without this type of charge separation that can occur, and the fact that water molecules can now interact with two more neighboring water molecules through these three different charge separation sites, gives water its unique surface tension, gives water its unique boiling point and freezing point. I mean, if we take away this interaction, water should be a gas at room temperature. Okay, so if we look at other things like water, so if we look at put a sulfur in instead of oxygen or selenium, those are gases at room temperature. Okay, so we couldn't have life without that aqueous water environment. It just gives it some very, very unique properties. Another example of a polar molecule is what happens with the structure of ammonia. Ammonia is an AB3, and it's an E because there's a lone pair of electrons on the nitrogen atom. So now what happens with this? It's trigonal bipyramidal, or it's trigonal pyramidal. So the NH bond is a polar bond. So you've got 2.1, and go over and count nitrogen. So fluorine's 4, 3.53. So the electronegativity for nitrogen is 3. So you're going to have a dipole moment for every bond going towards the nitrogen atom. But now when we start to add them together, the out components all cancel in. If I look over this from the top, the only thing that doesn't cancel out is there's a net dipole moment going up. The result is that ammonia is a polar molecule. Okay, so the big influence that we have is that the polarity of molecules start to interact with one another the same way that the poles of a magnet would. So polar molecules are attracted to other polar molecules. Water is a polar molecule, so it attracts other polar molecules to it and causes them to dissolve in it, as well as ionic compounds. We talked about the solubility rules earlier in the semester about some things would dissolve and some things would not. This is kind of the why things dissolve. So an example of a water molecule, the electropositive sites will line up with the electronegative sites. And if there are other types of molecules that have similar charge separation, things like alcohols, where there's a separation of the oxygen and hydrogen, causes the separation of an electropositive and electronegative, those are things that are going to dissolve in water well. And anything else that has similar bonding will do the same thing. When you have an example where there's a difference in the types of charge separations. So something like oil doesn't have charge separation. It consists primarily of nonpolar bonds. Carbon, hydrogen, carbon, carbon. Okay, so those are what we classified as nonpolar bonds. Electronegativity is less than 0.5. Because of that, there's no large dipole moments that exist. So if you mix water and oil together, you can shake them up all you want to. What you'll find is that the water separates to the bottom and the oil goes to the top. Okay, why does the oil float to the top? Density, yeah, it's a lower density. So if you're a mechanic guy or girl, you've got an older car and you think you've got a blown head gasket, so it's leaking water in the oil. There's two ways you can check it. So run your motor a little bit, pull your dipstick out. If it's milky white looking, okay, where the two things have been mixed up, you got water in your oil. If you let it set for a while and you get underneath the car and pull the oil plug out, and if water comes out first, milky white stuff, get plumb headed. Okay, it's the easy test you do. If you let it set for a while and oil comes out immediately, your head gasket's not blown. You got another problem, maybe leaking. But it's a simple test you can do to see if you got a blown head gasket. Now, some molecules, like soap molecules, have both polar and nonpolar regions, and that's what gives them their unique characteristics to dissolve things. So an example of the sodium stearate molecule, which is a common surfactant that's used in things like hand soap, shampoos, toothpaste, and a variety of different things. It has a polar head group that attracts water molecules and other polar molecules, and then it has this nonpolar region that attracts to nonpolar molecules. And the way that it works good as a soap is that surfactants will take, let's say that you've got on a surface this nonpolar molecule, and this nonpolar molecule doesn't want to be in water. So it's stuck to the surface of your fabric or your skin or wherever it may be. So this soap molecule comes along, and it will orient itself so that the nonpolar regions, this portion of the molecule, all attach to the nonpolar molecule, and that the region that is polar, right, the water-loving region, points out, and it will encapsulate this particular substance, and it will actually carry it away. So once that thing surrounds it completely, it will break it free and allow it to carry out to the system. That's the way surfactants work. All right. So it works on much in the same principle as the lipid bilayer works, except now instead of being two sheets of things, it becomes something that's circular, and it works at a much smaller scale. Okay, so let's practice with these and figure out if something's going to be polar or not. Just a couple more slides left. So let's look at these two molecules. So I've got this first one. It's an AB2E. So what is the geometry going to be for an AB2E? What's that? Bit? Right. So its electron geometry is trigonal planar, but we don't see those electrons, so it's a bit shape. Okay, so it's if we look at it in three-dimensional, it would be something like this guy. Now we have to look at the magnitude of these electron negativities. So I've got 3, 5, I've got 3, and 3, and chlorine is also 3. So these two, there's no difference, but on this one, there is a difference in electronegativity, so there's going to be a dipole moment in this direction. So the net dipole moment that would occur with this molecule would be something like that. So this would be something that is polar. Now, I'd say a little polar, and the reason I say little is because this difference is only 0.5. It's not a huge polar bond, but we classify that as a polar molecule. Okay, if we look at the one next to it. So this is an AB3, and AB3 is going to be what? Okay, so it's going to be trigonal planar. So as a trigonal planar, it's going to be a geometry where they're 120 degrees all laying in the same plane. Now if I look at the electronegativities, I've got sulfur's 2.5, the oxygens are 3, and that's the same for all of them. So if I look at the individual bonds, so this one has a electronegativity pull in this one, this direction. This guy's like this, and this guy's like this. But if I do my vector addition to it, what happens is this just has an up component. This one has a down component. This one has a down component. So put those two things together, their total down component completely cancels out with the up component, and their left-right components cancel out. This results in a nonpolar molecule. And the way that's most easy to see is their symmetry. When you have symmetry, you result in a nonpolar molecule. All right, so there's the example. Say again?
The types of bonds not matter. The fact it's a double bond. I know in that situation it's like rotating, or was that resonance?
And that's the reason it doesn't. Because in reality, that double bond is jumping around from atom to atom to atom, and it's sharing those electron densities between the three. So no, it doesn't. Okay. All right. There's some example questions off the old exams. We're going to do that later. So, all right. Let's figure out which one of these is a nonpolar molecule. So we're doing it as a group. I'm going to try to help you out a little bit. We're going to, as a group, do some Lewis structures. So we've talked about, so maybe we get the Lewis structures right, you can figure this out. We've talked about ammonia already. So there's its Lewis structure. You can work with that one. So xenon tetrafluoride. So I'm going to do the ones that I know. That's water. All right, so this is all right, so I got to figure out the xenon. All right, so xenon has 8. Each fluorine has 7. 4, 4, that's 28. So 36 electrons. That uses 8. That gives me 26. 6. Yeah.
What are you looking at?
That uses 24. Okay, so 1 lone pair is what I've got on that one. Okay, so are any of these nonpolar molecules?
I'm pretty sure the one you just drew.
Xenon chloride.
Okay. So did I do, if I count my electrons right?
Whenever you subtracted 8, you said 26, but I think it's 8. Then that would put an extra line 48 on.
Oh, it's should be another lone, should be a
AB.
Okay, it's an AB42, yeah. That makes more sense. Okay, so there's 2 lone pairs around the central atom. Okay, so I've done the hard work for you. There's the Lewis structures. This is a group problem, you don't talk about it, but figure it out.
Hey, Dr. Smith, what's that molecular geometry for the xenon that you looked at? Because it's like a square, but we don't see the electron cloud, right? The square.
Agree?
What's that
Okay,
word
so square planar.
called? Square planar?
Yep.
Okay.
So the opposing pairs of electrons are going to wave to each other. So regardless which side of the octahedral you go on, they're always going to be away from each other. Okay. All right, we're all in. So most of you like choice B. A couple of you don't. I like choice B. So let's use the process of elimination, how we can figure out if some things are polar. So this was our example of a polar molecule a while ago. Okay, so it's an AB3E. Okay, so you've got a lack of symmetry. That's going to be polar. So polar. Cross that guy out. A water molecule was our example of a polar molecule. It's got a net dipole moment in that direction. So kick yourself if you put B or C. Okay, so now if I look at this next one, it's the tetrahedron, which is symmetrical. The difference is that now you've got these swings in electronegativity. So you've got the chlorine, which pulls the electronegativity more than the other atoms. So there's going to be a net dipole moment towards the chlorine atom. So that one also is polar. And if you look at the one below it, now you've got 2 chlorine atoms substituted on there. You've got the same thing now. The electronegativity is greater for the chlorine atoms. So you've got a dipole moment small in this direction, so that's supposed to say 2.5, but then you've got a big pull in this one and this one. There's going to be a net dipole moment right between those two chlorine atoms going in this direction. This is called methylene chloride or dichloromethane. It's a common polar organic solvent that we use. Okay? All right. So that's how we kind of figure those guys out. So now we've done just a little bit of introduction with the Lewis theory in this chapter. It gives us a good approximation of what bond angles can be, but it's not perfect because of just all atoms are not the same size. They're usually good within a few degrees. Okay, but that's as good as we can get. So we can't write out using Lewis theory correct structures things where resonance becomes critical. Because of that concept that the electron density is shifting out between bonds, that causes a shift in the way that we line things up. So if everything's a single bond, yes, it works very good to predict. But when we start to get these double bonds that are jumping around from atom to atom, it's not so perfect. Okay? But we have to start somewhere in learning how to do these things. It doesn't predict correctly the behavior of some magnetic behavior of some compounds, like oxygen is paramagnetic. Lewis theory predicts it should be diamagnetic. And we'll learn about, and you get to organic chemistry and inorganic chemistry, more advanced bonding theories, things like molecular orbital theory, that start to explain these differences where Lewis theory did cover everything. You got to start somewhere. Lewis theory is our introduction to that. Okay, so that covers the material. All right, let's do one more. I'm here, just in case you missed on. So click anything. Don't click H, or whatever high number is. Okay, so, all right, so that'll give you another clicker question, and I'm going to close the clicker. Okay, so you clicked your last click for the year. All right, so clickers are on. So now let's spend a little bit of time talking about the final exam and what's going to be on that. So I posted the study guide for the final exam. You can go look at that. We are going to meet at 11:30, our regularly scheduled class time, instead of the normal final exam schedule is 11 to 1. But because some of you are concurrent high school students, we know the 11:30 schedule works, so that's what we're going to go with. All right, and there's no interfering exam going to start at 1 o'clock that's going to mess you up. So this works for everybody. So our final is going to be at that time. All right, the exam that we're taking is the ACS standardized exam. That's a 70-question multiple choice that's timed at 110 minutes. Time becomes important. Okay, so that means you've got on average a minute and a half to the most you can spend on a problem. So you can't sit and look at a problem for 8 minutes, or you're going to kill your grade. So this is part of your test strategy. We're going to talk about it for a second. The study guide's available, so I sold one to somebody a while ago. If you want one of those, it has a breakup by chapter of the topics that you should cover. It gives you example questions. Again, in no way do I require that you purchase this. It's a suggestion if you want to work on improving your grade. Here are the topics that are on that exam. So these are the things, for the most part, we've covered this semester. Dimensional analysis or factor analysis, you're going to be asked to do some of that. Understanding chemical formulas, both empirical formulas, molecular formulas, molar masses, etc. Nomenclature, so some naming. Balancing reactions and equations. Assigning oxidation numbers and what they mean. And then descriptive chemistry, things like solubility, acid bases, understanding that. The relationships in stoichiometry. Two things react. You consume so much of one reagent, how much does the other reagent take? How much product does it make? That also could go to percent yields, something like that as well. So all the things we've talked about. In solutions, molarity and stoichiometry. Thermal chemistry, something like calculating the heat. Okay, so specific heat, mass, change in temperature. Electron configuration, the quantum number rules we just got through talking about. The bonding we talked about in this chapter, ionic and covalent bonding. The periodic trends. ionization energies, electron affinities, the size of ions, the size of atoms, right? And anything else that we talked about in those trends. The thing that we just talked about at the end of this chapter, Lewis structures, being able to predict those, how to calculate formal charges, VSEPR theory. The things that we didn't talk about are the intermolecular forces. That's actually chapter 11 for us. If you want to study some extra, you can study ahead and look at chapter 11. And then the gas laws, which we covered quite extensively. So that's the things that are there. Again, the one thing that was labeled with a star is something we didn't cover, and that was intermolecular forces, which is chapter 11 and 12 in our textbook. Look ahead if you want to look over that material. The thing that I would tell you to do is read chapter summaries. Don't worry about trying to read the entire chapter, but look at key concepts that are there. Look over your old exams as you can. Try to understand why you missed something. Look at the summaries found in the Mastering Chemistry and the tutorial problems. Mastering Chemistry problems are all still opened up, so you can go look at those problems again, see what you answered or what you got wrong. You can look at your PowerPoints at any time. The thing I want to emphasize is this exam is it's 14% of your grade. It's about an exam and a half of exams. So if you're borderline, you can influence your grade in a positive or a negative way. And I'm going to show you some stats, what students did last year in doing just that. The big thing is where I got to be stringent on are the calculators as well as phones. Absolutely everything will be put on the back wall. You can't have a phone on you. These are copyrighted and protected exams. There's no way that I can let you do anything that somebody takes a picture of it and post it. Kids steal this information, post it on Keg. So college student, you probably know what Keg is. So you can sell those answers on Keg to test questions, and if you do, they prove it's you. The American Chemical Society will hold you financially responsible for replacing that exam. They've sued 3 people so far successfully. It's about $250,000.
Wow.
Yep. Yep. So it's not only is it the printing cost to every university, but the exam writing committee, we meet for about 3 years to write one of these tests. So we get together and we meet at a national conference like in Chicago or wherever it's going to be. We say this is what everybody's going to work on. There's usually a group of 12 of us that will get together on a committee from different colleges all across the campus or across the United States. And then based on that, we break into subgroups, usually groups of 3 or 4. We each write a dozen questions or so. We get them together in our subgroup, pick a couple of questions we like. Then we come together at another conference, usually 6 months or a year later. We devise a group of questions. We make preliminary tests. We send those out to colleges, let students take samples. Then we look at a statistical sampling of 3,000 or 4,000 students to say these are good questions versus bad questions. It's a very, very expensive process. I mean, the airfare alone, just flying us around, is $50,000+. I mean, that's the cost in these things. So they're protected, and there's a reason they're that way. Okay. You can't use a programmable calculator. So if you bring a TI-80, TI-90, I can't let you use it. So you got to get used to your old one. That's not a programmable there. We've already looked at that. So it's a multiple line scientific calculator, but you can't use, and you certainly are not going to use your cell phone. Okay, so here are some things that I found. This was somebody else's opinion, but it looked like a pretty good concept, so I copied this out. The goal is to understand how well that you understand what should be covered in a typical first semester chemistry and to have a comparison to how do you perform to other students across the country. So there's not a huge emphasis on math problems. So anything that's a detailed calculation, you're probably not going to have that. Some of you are going to love that. Some of you love the math part of it. The best way to review for the exam, and I think this is good knowledge, is to go over previous exams in our class, the end of the chapter type questions. If you haven't been looking at those suggested problems at the end of the chapter, this is a great chance to review some of those things. Look at the things that you understand versus things that you don't. with the 70 questions multiple choice, there's 4 choices with each ones, and there's no penalty for guessing. So you're graded on the number of questions that you get right. So if you skip one, it's not in your advantage. So like on the some of the exams, like when you take the GRE, if you skip a question, it calculates your score based on the number of questions you get right out of the number of questions you attempt. This one's not that. It's crude, total number of questions you get right. So the thing that's going to be given to you at the top and the front page, there's going to be a list of abbreviations and some symbols. There's going to be a few constants that are given, like the R constant. I think they expect you to know Avogadro's number. There's a few other constants that are given there. There's a periodic table. We're going to be in this room, so I'm not going to take these down. Some of the faculty members actually cover these things, but I don't do that. Here's the biggie. No equations provided. So I'm going to go over a simple list of equations here, and there's not that many things that you're expected to know. So the directions that are there, you can't write on the exam booklet. So those cost the university about $5 a piece to purchase those exams. If we write in it and we can't erase it with a pencil, you're going to be asked to cover the cost of replacement. You've got to write your answers on a Scantron with a number 2 pencil, so you need to bring a Scantron, a smooth Scantron, not the one that's in the bottom of your backpack all semester. Okay? So if it's wadded up, it won't go through the machine, and you're going to have to write on both sides of it. So 70 questions, you're going to do front side and back side of it. When you do that many questions, it's important to occasionally look and make sure question 34 is really question 30. If you get off, you kind of got to start again. It's too much to erase. Any calculations that you need to do, you can do that on scratch paper. That'll be given to you. And there's only one correct answer for each question. So hopefully it's going to be clear to which one that is. And it's your advantage by the end to put an answer for every question. Don't leave anything blank. Even if spell your name out in letters. You got to put something there. If you put multiple answers on one question, it will not give you credit for either of them. Okay, here's the strategies. Don't allow yourself to get stuck on a problem. Make sure that you have time to answer everything that you know how to answer. So as you're working the question or the exam, go through and quickly do all the problems that you immediately know the answer to. All right, if you skip one, write it down on your scratch paper. Write that one down. And then you come back and you start working the ones that you know how to do the most. Next time you didn't know how to do those, the time allows. And then the things you're really going to have to think about, save those for last. Now, where that requires organizations, you have to keep that list, cross them off, and then make sure you transfer the answers back onto the Scantron. So there's some things that you have to do to make that work. But what you don't want to do is leave 20 questions at the bottom that over things that we just talked about in Lewis theory and Vespers that you know the most that you never got a chance to look at. All right, make sure that you look at the entire exam, because at 110 minutes, I'm going to say pencils down and take the test up. All right, so everybody else in the country is doing the same restrictions. So your score on your final depends on your percentile ranking, and I'll talk about how that's going to work in a second. So actually, I don't do a percentile ranking. I choose a certain percentile. So I choose about the 70th percentile, and I choose that score to be what I call 100. So you're just being compared to what students can do across the country, understanding that some students do much better, some students do some worse. So you can write several pieces of scratch paper. If you want multiple sheets, I have no problem doing that. Don't worry about that paper is just going to be taken up and being shredded. You can't leave with it. What you need to do is spend time studying for the things that you know. You spend less time studying for the things that you know and emphasize the things that you don't know. Right? So just kind of plan ahead, and you got to balance that with everything else. So here just gives you an idea of what the stats are for our exam. This is the national norms. So I'm typically looking right in here. So 46-47 will be our 100. In fact, I've said that 46. Okay, so that's the 46 is the 67th percentile national ranking. So if you score above that, that means you've got 100. Here's what my last year's class did. So had one student make a 54 in the class, so that's 118 on the final exam. I had a couple of students make right at this, so they got right at 100. But even the class average was a 31.9. If you divide that by 46, that came out to right at a 70. Okay, so this is just up to you on the effort that you want to put into it. The low score that was made in this particular year was 21 divided by 46. So, yeah, you can make a 50 on it or less. But that student was kind of stood out from the rest of the group to some extent. You can improve your grade. You can hurt your grade. It depends on the effort that you put into it. Okay, here's kind of my list of things that I suggest that you know. Common strong and weak acids and bases. At least remember something about the solubility rules, in particular which ions at which there's no exception to the rule. When I say that, know that the potassium salts are always soluble. The nitrates are always soluble. And the common things that are insoluble. There's a couple of things that are things that would stand out to help you ask a question. Things that we talked about with energy. What it means to be a state function, an extensive versus an intensive property, enthalpy, how to apply Hess's law to calculate an enthalpy for something, and then specific heat capacity, so you can calculate the energy change associated with a mass and change in temperature. How to assign oxidation numbers, all right? And then the rules for what's an oxidizing versus reducing agents. Go back and remember way back from chapter 2, what the heck of an isotope is. All right, and what those symbols mean for the mass number, atomic weight, subatomic particles, how many protons, electrons, and neutrons are in a particular atom. All right, chemical and physical change associated with properties, significant figures, the standard metric units as well as prefixes, some nomenclature that you'll be asked to do. You'll be asked to name something. You're going to probably be asked to, given a name, choose a formula, and you're probably going to be asked, given a formula, choose the correct name. All right, so you'll probably get some for ionic, some for covalent compounds. They're not going to be huge, complex compounds, but you have to understand those common namings that we have. You'll have to take and predict a composition or a ratio. So based on where an element is in the periodic table, either not using known charges or what the Lewis theory suggests, what would those elements combine to make a molecular compound or an ionic compound. You're going to be asked to complete or balance an equation. It may be a combustion equation. It could be something like a net ionic equation. We didn't use the terminology double replacement. That's that means you just basically swap the ions from one side to the other. That's the terminology we don't use much anymore. But gas reactions, spectator ions, things like that, we did talk about. The basis of stoichiometry. So molar masses, mole ratios, limiting reactant, percent compositions, molarity, percent yields, empirical molecular formulas. We talked about all that stuff over the course of the semester. The gas laws, the simple gas laws, the ideal gas law, partial pressures, standard temperature and pressure, the idea of what's happening with molecular motion with changes in temperature, change in pressure. That's called the kinetic molecular theory, as well as the way barometers and manometers work. And then we start talking about energy associated with electromagnetic radiation, frequency and wavelength, spectras, electron configuration, orbital diagrams, just tested over, as well as the common quantum numbers, the trends in the periodic table, and then we get down at the end, we're talking about Lewis structures, the resonances, formal charges, bonds polarity, exceptions to the octet rule, and bond order. We'll talk about bond order next semester when we talk about bond order. And then finally, the last thing is VSEPR. We didn't cover hybridization. That is the topic on the test, but it takes a long time to cover that. You'll get it on organic. So not everybody nationwide sees all this stuff. Polarity of molecules we talked about today, lone pairs, bonding pairs, sigma and pi. We didn't cover that. That's the advanced theories. Just realize things like the gas constant R, which has units of liters, atmospheres over moles, degree Kelvin. It may be written something like liters, atmosphere, moles to the -1, degrees Kelvin to the -1. Those two things are equivalent expressions. Okay. It's just that it's easier to write something like this than to set up a formula when you set it in text. Okay, here's the simple formulas you need to know. All right, so I tell you at minimum, know these guys. The density formula. All right, the dilution formula. Concentration times volume equals concentration times volume. The ideal gas law, PV equals nRT. All right, the heat equation. Heat is equal to mass times specific heat times delta T. All right, and these are on the video. You can go back and watch these if you want. I'll post it. How to calculate molarity. So how to calculate molality. What the difference in those two are. Molalities, instead of per liter, it's per kilogram of solvent. Percent composition, mole fractions, we talked about those. You could do a combined form of the ideal gas law to set the common variables that change. So if it's a fixed volume or a fixed container, so the number of moles doesn't change, and you can change any combination of temperature, volume, and pressure and predict what it would be the new temperature, volume, or pressure. All right, if the number of moles of gas stay the same. But that's nothing more than an application of PV equals nRT. So I don't know if that's a separate system you need to know. Remember that when you have a change to the surroundings, that the energy lost by the system is equal to energy gained to the surroundings. Okay, so the system and the surroundings make up the universe. You'll probably do something with Hess's law. In some way, given something about bond energies, have to predict the enthalpy of a reaction. Yes?
They're going to give us the specific values for those?
They have to. Yeah. Yeah, there's no way that we expect you to know that a C double bond C is this bond energy. There's just too many of them to remember. Nobody remember it. Well, I'm sure there's somebody that does, but nobody I know does that. Here's the types of things you're going to get. So this is the table that's at the top of the page. So it's going to have some specific things in here that talk about some abbreviations, and those may be used in various questions. And it's going to give you some common constants. And even we talked about multiple types of R. So the gas constant R versus the thermodynamic R were two different R's that we used. We didn't do anything with electrochemistry, so Faraday's constants wouldn't be things we have. It does have Avogadro's number in there. It's got Planck's constant, and it's got the speed of light. So those are probably going to get the same set of constants given to you. All right, there's going to be a crude periodic table at the top. So that's what was underneath this, was the periodic table. And I'm just going to spend a few minutes to show you just a couple of example questions off of it. This is a retired exam. This one's from about 20 years ago. And this is a full semester's worth of chemistry. It's not just Gen Chem 1. At that time, they weren't writing a first semester and a second semester. But just show you the types of questions that you're going to see. Some are going to be pictorial in nature. Let me go so we can get the full page there. Some are going to be pictorial in nature. And you can't see that. Lost my stool. There it is. All right, some are going to be, just going to go up and down I can scroll up and down. Which represents a formula for hydrogen? Which is a physical change? And then, which is the correct name for an acid? All right, so know your common acids now that we talked about. How many atoms are in a particular compound? So, given this name, what does that mean in terms of a formula? How many atoms are there? Read your ruler. Right? There are going to be some serious, simple questions as simple as estimate this object's length and how accurate could we know that? Questions like, given a set of data, what does that tell you about accuracy versus precision? So we talked about that in things like data. You've got something that's, you've got a certain amount of energy, and it tells you the calories per minute, how much kilojoules per hour, so that's factor analysis. It's conversion of units, and you're given the relationship. Here's something with density. You're given a volume, and you want to know what has the same mass of something else that's got a certain volume. So acid-base reactions. So what would you neutralize phosphoric acid with? Here is what's the net ionic reaction that's happening between two ionic compounds. Identify the oxidation number for an element. Which one's the precipitation reaction? And take a look at that one. That should be something you answer in 5 seconds. What are you looking for in that? Solid. There's only one that's got a solid as a product. It should be that quick. Okay? Just understanding that. Same if it's a gas forming reaction. If it's an acid base, what's the products of an acid base reaction? Water and a salt. Okay? So those things should be able to do really quick. All right, so what's the formula that results from a combination of iron 3 and sulfate? You've got to know what sulfate is. Okay, so you got to know your common polyatomic ions. What happens when a metal reacts with water? What's the products? Which would be the least soluble in water? So solubility rules. Which one is the empirical formula and molecular formula the same? Try looking. Balance in a reaction. Okay, so how many moles are in a certain mass of a compound, given the molar mass? How many moles of a product are made, given amount of a reactant? Okay, what is the mass composition of a certain compound? So on this one, it wants to know how much mass is potassium. This one. Which balance reaction gives you no evidence of a reaction? So everything basically is a spectator ion. Nothing happens that's obvious. So when a gas is produced, everything stays in solution. Calculate a percent yield. Two things react. How much product's going to be made, or how much excess reagent is left over. So you have to figure out which one is in excess and how much of it's left. So that's just stoichiometry. How many, this is a CV equals CV, how many milliliters of a higher concentration does it take to make a certain volume and concentration of something more dilute? What equipment would you use to measure something with? So those are the types of questions that you're going to see through this. Some things is, here's an example like the bond energy one. So if you're going to use Hess's law, here's the reaction. You have to figure out what type of bonds you have in the Lewis structure. And then the bonds broke, bonds formed. Okay, subtract the two from one another. So much like we just did on the test. Know your isotopes. So you got the sodium 23 plus cation. How many protons, electrons, and neutrons are there? Some things like the history we talked about. What did Rutherford discover in his experiment? Okay, so what did Rutherford do? It's just over everything that we talked about this semester. So I encourage you not to choose which set of quantum numbers is allowed versus which ones are not. Relationships between the size of the ions and lattice energy in ionic compounds. There's very, very few things on here we didn't talk about. And again, this is not going to be our exact test. This is just an example. Things like hybridization, we didn't talk about that, but you're talking about maybe a couple of questions. VSEPR stuff. Okay, so which one's going to be the correct? This is actually just a molecule we did a moment ago. So that guy we said was a square planar D. Sometimes they're going to be pictorials, so understand what's happening in a picture to describe what we think is going on. Calculate the dipole moment, which one has a net dipole moment versus which one doesn't. Again, you're looking for symmetry, things like that. Back when we talked about with gases, be able to look at what a barometer says and how to interpret what that means. Okay, so that's just the 1, 2, 3 of what we're doing. You can go back again and look at that stuff. You can watch the video, and I'm going to stop the video for you to do that. Other thing,